Hello. In this video, we're going to look at limits part 3, and we're going to look in particular at one-sided limits. Now, to begin with, we need to make the important remark that some limits do not exist. You might remember from one of our earlier videos in part 1 how we showed using a calculator gave us the wrong answer because one limit didn't exist. That was quite a complicated limit. Here we're going to dial it back a little bit and look at some very simple limits that still fail to exist. In particular, we're going to consider a very famous function called the Heaviside function. This was developed by Oliver Heaviside. He was a physicist and an engineer about 150 years ago, and so we're going to look at his function, h of x, which is equal to either 0 when x is less than 0, or 1 when x is greater than or equal to 0. Now, this function here we can draw. It's not too challenging to look at. We would have 0 when x is less than 0. So it would be just like this along the axis with a hole right there. And then 1 when x is greater than or equal to 0. Sometimes this is called a step function because it looks like a little step on a staircase. So it's 0 down here and then 1 over here. Now we want to consider the limit as x approaches 0. What that means is we're taking values that are closer and closer and closer and closer to 0. So we could take, for example, 0.1 or 0.01 or 0.001. And if we took positive values, well, we'd be taking this portion of the piecewise function. So we'd be taking, 1. And so if x was equal to, you can imagine here, 0.1, the y value is going to be 1, or 0.01, it's still going to be a y value of 1. In fact, if you even plugged in 0, you would get a value of 1, because when x is equal to 0, the Heaviside function is 1. But when you do the limit, you're also supposed to try some negative values too. You're supposed to approach 0, and so you could approach 0 from positive values, but you could also approach from negative values. Well, if you did negative 0.1, that's going to be 0 there on the graph. Negative 0.01 is also 0. And so it appears that as you approach, 0, it appears that you get both the value 1 and the value 0. If I was to say what's a logical value to fill in right here, some people might say a logical value is 1. Some people might say a logical value is 0. It's hard to say. It kind of looks like 1. It kind of looks like 0. Maybe a half. There's really no consensus. And so because of that, because there's no logical value, we would have to say here this limit does not exist. Sometimes we write DNE for short. Does not exist. Now, we can be a little bit more precise in terms of how it's not existing. And to do that, we're going to talk about one-sided limits. So, as a definition, we suppose fx approaches a real number L. As x approaches a from the left, we would write this as limit x approaches a with a little negative sign on the a, f of x equals L. This is called a one-sided limit. And what it looks like in practice is you have your number a that you're approaching. And what you do is you approach from this side. So you go from the left. So maybe here, 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 here. You approach from the left of a. And if as you approach from the left of a, you get some number, L, well, then that would be the limit from the left. Similarly, suppose that fx approaches a real number L as x approaches a from the right of a. We would write this as x approaches a with a little plus sign, f of x equals L. So in this case, here's our a value. And we would approach here from the right. Now this is exactly what we were doing in the example above. If you look here, we were considering as we took positive values or as we took negative values. This here is approaching 0 from the right-hand side, because here's the number 0 and we're approaching from the right. And this is approaching 0 from the left-hand side. So this is technically a right-hand limit or a left-hand limit. Right side or left side. So let's go ahead and see what we would get. For the limit as x approaches 0 from the left of the Heaviside function, what that means is we're doing x approaching from less than 0, which clearly gives us 0 as a value. It's 0, 0, 0, 0 all on the left-hand side. And as x approaches 0 from the right, it's clearly 1. And so both of these limits exist. The left-hand limit exists and the right-hand limit exists, or the left side and the right side both exist. But if you notice, these two, they are different. And that's very important. On their own, as a one-sided limit, each one exists. But together, they're going to tell us something very important. And what they're going to tell us is that there's a criteria for existence. For an overall limit to exist, it exists if and only if the limit as x approaches a from the left of f of x equals L equals the limit as x approaches a from the right of f of x. In other words, you need the two limits to give you the same value. Otherwise, the overall limit does not exist. So just to recap on our example there, the limit as x approaches 0 from the left of the Heaviside function equals 0, but the limit as x approaches 0 from the right of the Heaviside function equals 1. Therefore, the limit as x approaches 0 overall of the Heaviside function does not exist, because 1 is not equal to 0. Now let's look at a diagram and try to do some examples. Here we have a graph, and we're going to try to find the limit as x approaches 2 from the left, 2 from the right, and 2 overall, 5 from the left, 5 from the right, and 5 overall of our function g of x. All right, let's take a look as x approaches 2 from the left. So what that means is here's our value 2, and we're going to approach it from the left of 2. As we do that, what does it appear like the y values are approaching? Oh, it looks like they're approaching 3. So we could say the limit as x approaches 2 from the left of g of x equals 3. How about as we approach 2 from the right? So as we go from the right, it appears like the y values are approaching 1. So we could underneath write this as the limit as x approaches 2 from the right of g of x equals 1. But if you notice, these are not equal. Therefore, the limit as x approaches 2 overall of g of x does not exist. Let's try over at 5. So as we approach 5 from the left, it appears like the y values are going to approach, well, 2. As we approach 5 from the right, it also appears like we're going to get 2. So the limit as x approaches 5 from the left of g of x equals 2. The limit x approaches 5 from the right, x approaches 5 from the right equals 2. And these are equal. So therefore, the limit as x approaches 5 overall of g of x equals 2. That limit does exist. Now again, it's important to note that limits and function evaluation are technically different. If I was to ask you what is g of 5, well, g of 5 looks like it's 1. And if I asked you g of 2, well, that's actually undefined because there's no point there. So the function definition is going to be slightly different from the limit. When it plugs in nicely on a nice function, then of course you get the same value, but you should start to see here that there are slight differences. In this case, again, the function doesn't plug in. You get one-sided limits existing, but the overall limit doesn't exist. In this case, the function does plug in, but it plugs in at like a weird value here. And so the limits exist and equal 2, but it doesn't actually equal where you would plug it in as. So keep in mind on that, and we'll investigate that more as we look at future examples. Now, just as a remark, we usually use one-sided limits to evaluate the limits of piecewise functions or absolute value functions, because absolute value functions, as we'll see in a bit, are, of course, piecewise functions in disguise. So we're going to go ahead and try this example here and see what we come up with. So f of x is equal to 2x squared minus 3x plus 7 and 2x plus 5. Again, this is a piecewise function, and I think about it as a piecewise function because it literally comes in two pieces. So let's see what we would get for our limit. So we want to do the limit as x approaches -1 from the left. So limit x approaches -1 from the left of fx. And to do that, what it means is we're approaching -1, we're taking values less than -1. Which means, which portion of the piecewise function are we using? Well, if we're going to the left of -1, we need less than -1. That's going to be this portion here. So we can substitute that in for fx. 2x squared minus 3x plus 7. Now, that limit doesn't need any kind of fancy factoring. It looks like something we can just plug in. So we'll get 2 times -1 squared, which is going to be 2 times 1, minus 3 times -1 plus 7. So 2 plus 3 plus 7, that's going to give me 12. Now let's do the limit as x approaches -1 from the right of fx. So in that case, x is going to take values greater than -1, which means we're looking at this piece of the function, so 2x plus 5. So x approaches -1 from the right, 2x plus 5. That's going to give me 2 times -1 plus 5, which is going to be 3. These two values, of course, are not equal. So therefore, the limit as x approaches -1 of fx does not exist. Now, what I want you to do is see how this looks on a graph. I want you to visualize this. So we're going to pull up Desmos and look at this piecewise function on Desmos. So here we have the two functions graphed on Desmos. And one thing to note, you can use Desmos for graphing piecewise functions. You just graph the two functions as two individual pieces, and then you include curly brackets for the domain. So x is greater than or equal to -1 for that second portion, so you put curly brackets and put the restriction on x. Now if you look here, you can clearly see that the limit doesn't exist. As we go from the left, it looks like we're getting a value of 12, which is what we found. And as you go from the right, it looks like you're getting a value of 3, which, of course, is not the same as 12. And so you can see clearly here, as you approach from either side, you're getting different values, so the overall limit doesn't exist. Now, just for fun, I'm a little curious. It looks like this line can maybe be moved up so that they do join up, and so the limit does exist. What number do you think we'd have to change this 5 to make the limit exist? Go ahead and pause the video, or maybe try typing this into Desmos yourself and see if you could figure out what number you need here so that these two line segments, or I guess this is a parabola and this is a line, to show how these two would line up and get the limit existing. All right, so hopefully you gave it a try or gave it some thought. Let's see what we could do. Well, I could certainly try increasing this 5. If I made it maybe a 10, it looks closer. And in particular, the limits were 12 and 3, so they were actually different from each other by 9. So if we moved it up, instead of being at a +5, if I moved it 9 more, well, that would give me 14. And there you go. The two graphs would then meet up perfectly, and of course the limit would now exist and equal 12. So let's try a multiple choice question here. Use the graph below to find the limit as x approaches -2 from the left of fx. So hopefully you gave it a try. In this case, as you approach -2 from the left, clearly you're getting a value of -4. So the answer is C, -4. Let's try a more complicated piecewise function. In this case, we have 3 pieces. And what we're going to do is evaluate the limit as x approaches 1 from the left, 1 from the right, and 1 overall, 2 from the left, 2 from the right, and 2 overall. So let's go ahead and start with the 1. So we have the limit, x approaches 1 from the left, which means we're taking values less than 1. So for less than 1, we're going to be in this portion here, 2x minus 1, which will equal 2 minus 1, which is 1. limit x approaches 1 from the right, means we're taking values greater than 1. Now, this is a little technical here. As we take values greater than 1, well, technically this portion here is where x is greater than 1. But here x is greater than 2, which is also technically greater than 1. So am I using this portion or this portion? Well, when I do a limit, I do need values greater than 1. But I don't need them like 3 and 4 and 5. I'm picking values still close to 1, like 1.1, 1.01. And so I'm using this portion here. It's greater than 1, but it's close to 1. So it's going to be the x squared. 1 squared, of course, is 1. These two are equal. And so therefore, the limit as x approaches 1 over all of fx, it exists and it equals 1. Let's try 2. Limit x approaches 2 from the left. That'll be x squared, which is 4. Limit x approaches 2 from the right. That's going to be 2x cubed minus 12. 2 cubed is 8 times 2 is 16, minus 12 is 4. These two are also equal. All right, so therefore, the limit x approaches 2 of fx, it exists and equals 4. So both limits existed in this case. Now let's try one here that involves absolute values. So I want to look at the limit x approaching negative 3 from the left, negative 3 from the right, negative 3 over all, and here's our function. Now initially it doesn't look like a piecewise function, and so it's hard to say which piece you're going to choose. But that's because the absolute value here is a piecewise function, but it's a piecewise function in disguise. So we need to do this over on the side here. We have absolute value of x plus 3. If I rewrite it as a piecewise function, it's either x plus 3 or it's negative x plus 3, depending on whether x plus 3 is positive or whether x plus 3 is negative. Now, that looks a little bit messy, and I'm approaching negative 3. This portion here, you always want to clean this up a little bit. So I'm going to move the 3 to the other side, and then move the 3 to the other side. So that'll give me either x plus 3 when x is greater than or equal to negative 3, or negative x plus 3 when x is less than negative 3. All right, that should clear it up. When I'm going to do my limits from the left or from the right, I can look at this portion here, and it should help me decide how my function's going to look. So we're going to have the limit x approaches negative 3 from the left. That means we're taking values less than negative 3. So we're taking this portion here. So the top will be just the same, but the absolute value now, we're going to replace it with this portion here. So we'll have x squared plus 2x minus 3 over negative x plus 3. All right, well, if I tried to plug this in, I'm going to get negative 3 plus 3, which is going to be 0. There's a negative in front, so I guess negative 0, but that's still 0. So I have 0 on the bottom. If I plug it into the top, I get 9 minus 6 minus 3. That's going to be 0 as well. So I have 0 over 0. I need to do some more work. But it looks like factoring is going to help me out here. So let's try to factor that numerator. So here I'm going to get, just going to make some more space here. The limit x approaches negative 3 from the left, x plus 3 and x minus 1 over negative x plus 3. So that'll give the limit x approaches negative 3 from the left. We could cancel these out and give us x minus 1 over negative 1. Just watch out, there's a lot of negative signs here. 1 here, 1 here, and here, so maybe add some extra brackets there. And now we can try to plug it in. So negative 3 is going to plug in here as negative 3 minus 1, which is negative 4, over negative 1. So we're going to get negative 4 over negative 1, which gives us 4. So the limit as x approaches negative 3 from the left was 4. Now we're going to go ahead and do the same process as x approaches negative 3 from the right. So we'll just box that off there. And now we'll do the limit x approaches -3 from the right. Well, the top is still going to be x squared plus 2x minus 3. But the bottom is going to be, well, we're approaching -3 from the right, which means we're taking values greater than -3, so we're going to use x plus 3 on the bottom. Again, if you were to plug this in, you're going to get 0 over 0. So you're going to need to factor. The top factors, just as before, x plus 3 and x minus 1. The bottom has an x plus 3, which we can cancel. That'll give us the limit x approaches -3 from the right of x minus 1, which is just going to equal -4. Now what that means is that the limit on the left-hand side is not equal to the limit on the right-hand side. These are not equal. So therefore, the limit as x approaches -3 over all of f of x does not exist. So let's go ahead and try a multiple choice question here. Determine the limit as x approaches 2 of f of x given the following function. Alright, so I'm assuming you gave it a try. To find x approaching 2, because we have a piecewise function, we need to do the left and the right. So the limit x approaches 2 from the left means we need to look at the 3x plus 1, which is going to give us 2 times 3 plus 1 is 7. Then we do the limit as x approaches 2 from the right, which means greater than 2. So we take the x squared plus 3. 2 squared is 4 plus 3 is also 7. These are equal. So therefore, the limit as x approaches 2 over all of fx is equal to 7. Again, notice this slight technicality. As you plug in the value 2, you get 8. But limits aren't entirely concerned with what happens when you plug it in. We're all about approaching from one side or the other side. F of 2 could be undefined, f of 2 could be 8. It doesn't really matter what it is in the piecewise setup, because all that matters is what happens is you approach from the left or from the right. So 8 is kind of irrelevant. So for homework, you can go ahead and try on page 92, number 4 to 7, and 15 through 18. That should give you some good conceptual understanding of limits. And then for an actual problem, you can try the following function. So f of x will be x squared minus 4 over 3x minus 6 when x is less than 4, and root x when x is greater than or equal to 4. And you can find the limit as x approaches 4 of fx. And to check your answer, you can go ahead and plug this function into Desmos and see if you got it correct. So hopefully you enjoyed that video, and as always, thanks for watching.